Good morning! Today we will be discussing inelastic head-on collisions.
Flippin' physics!
To begin analyzing inelastic head-on collisions, let's take a look at an inelastic head-on collision between two carts. In an inelastic collision, kinetic energy is not conserved because of it being lost to thermal energy, friction. Steve, can you explain to me what quantities are being measured and why?
That is rather simple, Mr. S. Mass and velocity are the two quantities that we are going to be measuring. And we are measuring those two quantities because the equation for momentum is P momentum is equal to m mass times v velocity.
Yes, great explanation, Steve. Let's store that in our handy-dandy toolkit. Stefan, can you briefly explain how these quantities are being measured?
The mass is definitely being measured via a scale, and the velocities are being measured through a photo gate, which our friends are using to find the position versus time graph in Logger Pro, and using the slope of that graph to find the velocities.
Yes, absolutely. Steve, can you please explain to me how we can calculate the initial momentum of our system?
The equation for initial momentum is the mass of object 1 times the velocity initial of object 1, plus the mass of object 2 times the velocity of object 2 initially, with numbers, that is 0.52 kilograms for the mass of object 1, negative 0.44 meters per second for the velocity initial of object 1, a mass of 0.995 for object 2, and a initial velocity of object 2 being 0.71 meters per second.
When we were initially talking about our conservation of momentum equation, I had made a mistake. Now, do not let this get you fooled. This equation is correct. However, because our circumstances are that we are examining an inelastic head-on collision, the keyword here being inelastic, our final part of our momentum equation is incorrect. Our two masses are now joined together in the final stages of motion because of the magnets. That is why this is an inelastic collision. These two objects collide and stick together, so their masses in the end should be 1. So that means that it should have a common mass, mass 1 plus mass 2. And because they are moving together, that means that their final velocity goes for both of them. So, in fact, this equation is what should be examined.
So, the equation for final momentum is mass 1 plus mass 2 times the final velocity. And with numbers, that would be 0.52 kilograms plus 0.995 kilograms times 0.23 meters per second, giving us a final velocity of approximately 0.35 kilogram meters per second.
Stevie, can you please tell me what the equation for our percent difference is?
The equation for percent difference should be percent difference is equal to the difference between our momentum initial and our momentum final divided by the average of our momentum initial and our momentum final.
After plugging in our values, we have a percent difference of 17.93%. And while that number may seem large, there are reasonable ways to explain why we have such a large percent difference. We will explore reasons why this value is the way it is when we discuss whether or not kinetic energy was conserved in our system or not. Steve, can you please tell me the equation for kinetic energy?
The equation for kinetic energy is 1/2 the mass times velocity squared.
Alright, good. So, let's have that in our handy-dandy toolkit. Okay, so, in a similar manner to how we solve for our initial and final momentum, we will take those same principles and apply them to our initial and final kinetic energy. Okay, so, please, Stevie, put in some numbers to our equation.
So in your equation, let's take the initial mass and velocity of object 1, which is 0.52 kilograms and negative 0.44 meters per second. And for our kinetic energy of object 2, we can take the mass of object 2, which is 0.995 kilograms, multiply that by the velocity of object 2, which was 0.71 meters per second.
Okay, so let's follow the second principle for our kinetic energy final. Stefan, take it away.
So for the numbers of our kinetic energy final, we can use the data table provided to us via our friends, and we know that based on that, the mass of object 1 is 0.52 kilograms, the mass of object 2 is 0.995 kilograms, and the velocity of both of the carts together is 0.23 meters per second. And when we place that into the equation, we have 1/2 times 0.52 plus 0.995 times 0.23 squared.
So class, based on our calculations, we have an initial kinetic energy of 0.30 joules and a final kinetic energy of 0.04 joules, meaning that kinetic energy is not conserved because the difference between the two is so vastly large. So class, can any of you tell me why this is the case?
There are many reasons why that kinetic energy is not conserved, but the main one here, I think, is friction and the jolt caused by the collision. Friction, we are considering negligible. In their collision, the jolt will cause a major loss in kinetic energy.
Stevie, yes, you are 100% correct. What do you think our friends in the experiment did wrong?
Mr. S, I don't think anything went necessarily wrong in the experiment. I do think there are certain things that could have been executed a little bit better, though. Steven from the experimental team told me that they did not consider the table needing to be level when they did the experiment, which could explain why some of our values are slightly off. Furthermore, they did not consider friction. Even though they used a frictionless track, there is still friction between the wheels and the track. So all those could be the explanation for our slightly off values.
Yes, you are correct. Now, I hope you have a better understanding of inelastic head-on collisions. Thank you for learning with me. I enjoyed learning with you.